So let's continue chapter 6. Okay. So what did we learn last week? Do you remember? We talked about expectations and standard deviation and variance, right? So we learned some properties, right? So let me ask you one question. So I have a random variable x. I know the standard deviation is equal to 10. Okay? So my question is, what is the standard deviation of negative 2 times I? What is the standard deviation for that? Anyone still remember? So x is our random variable, and it's equal to 10. And I want to know if I multiply the random variable by negative 2, what's going to be the new standard deviation? What's that? Negative 20? Okay. So we have one of the negative 20. Anyone else? So this property. So if we multiply the random variable with a constant, no matter if negative or positive, when we take the constant out, we have to use the absolute value. Okay? So that's why this is equal to the absolute value of 2 times the standard deviation of I, which is equal to 20. Okay? That's one of the properties. Okay? So we have other properties. We will not discuss those things in detail. Okay? Then we discussed some distribution models. Okay? The first one is discrete uniform distribution. Okay? That's the first model we discussed. So for the discrete uniform distribution model, every single value is equally likely. Okay? And that's the probability. Okay? So let me ask you a question. So we have this row sheet, right? We have 42 students on the list. So if I randomly select someone, so what's the probability that the randomly selected student is from the first 3 on the list? So let me repeat that. So we have 42 students. If I want to randomly select one student, what's the probability that the randomly selected student is from the first 3 students on the list? One over 42. So, Jonathan, right? So, what's the probability you will be selected?
The same. 1 over 1.
Okay. So my question is, what is the probability that the randomly selected person is from the first 3 students at the list? So it could be the first one, could be the second one, could be the third one, right? Then what's the probability? So everyone agrees that everyone has the probability to be selected as 1 over 42, right? So because we are talking about discrete uniform distribution, right? Then I have 3 choices. Right? So what's the probability that the selected student is from the first 3?
3 over 42.
3 over 42. right? So that's the answer, 3 over 42. So because each person has a probability to be selected as 1 over 42. And what's the event? So if we define, okay, the first student is Marcus. Okay. Marcus is not here. So he has the probability to be selected as 1 over 42, but we have 3 students here. So we have to multiply 1 over 42 by 3. Okay? So that's one application. So we may have this kind of problem in our homework and that. Okay? So that's a uniform distribution. Okay? Then we talk about Bernoulli trial. Okay? Some properties about Bernoulli trial. Okay? Then based on this Bernoulli trial, we started to talk about some distribution models. And the first model we discussed is, what is the model we discussed based on Bernoulli trials? Geometric model, right? So what is the geometric model about? Yeah.
The random value, they count the numbers, whatever trial.
So in the geometric model, let me put it that way. So we are interested in the first success, right? So a random variable that counts the number of Bernoulli trials until the first success. Okay. So we have several trials, Bernoulli trials, and we are interested in, so what's the probability that the first success will happen at the third trial or the fourth trial and so on and so forth. Okay. So if you are given a description and you see a keyword like first something, okay, that is talking about geometric model. Okay, so that's the first model based on the Bernoulli trial, and we have this what is that? It's a probability what function. When we talk about discrete random variable, probability mass function, right? Okay. The PI mass. Okay. This is the PI mass. Okay. And some properties. Okay. Then the second model. Okay. Second model based on the Bernoulli trial. That's a binomial model. Binomial model. So in the geometric model, we are interested in the first success. But here, for this binomial model, we are interested in the number of successes. Okay. Still, we have a bunch of Bernoulli trials, but we are interested in the number of successes. Okay. For example, I toss the coin for 10 times, and I define tossing a hat is my success. So I'm interested in what's the probability that I have 5 hats out of the 10 trials. Okay? So this could be one example. Or if we continue with the example we started last week. So the salesperson make presentations and want to close some deals. And he made 10 attempts. Okay? What's the probability that he closes 4 of the presentations or the deals? Okay? So that's what binomial model is talking about. So the number of successes out of the total number of trials still is based on the Bernoulli trials. Okay? So for this model, as you can see, we have 2 parameters, n and p. So n is the total number of trials. I toss the coin for 10 times, n is equal to 10. Okay? The salesperson made 20 presentations. Okay? So n is equal to 20. N is the total number of trials, Bernoulli trials. And P still is defined as the probability of success. What's the probability of holding ahead? What's the probability that the salesperson closes a deal? Okay. So that's the two parameters for binomial distribution or model. And this is, and K, we have a K here, and this is the PMF, the probability mass function. So it means, what's the probability that the random variable is equal to K? Okay. What's the probability I see K successes out of n trials? Okay. So this is the probability mass function. So if we look at this function, we have this n choose K, right? We have total number of n trials, and we are interested in K successes. So this is n choose K. So we will have a detailed expression for this one. Okay. And P, the probability of success. Okay. And Q is equal to 1 minus P, right? The Q is the probability of failure, 1 minus P. So because we are interested in K successes, so in the expression we have the P to the power of K. Okay? Because P is the probability of success, we have K successes. And then we have n minus K. That's the number of so-called failures. Okay? So it's Q to the power of n minus K. Okay. So this is the probability mass function. So let me go to the next slide. Okay. So this is the expression for n choose K. So we'll learn the combination. So this is the expression you use for the combination. And it's equal to this n factorial. N factorial is the product of n minus 1 and q 1. Okay. So this is the expression for the n. Okay. So when we do the homework, when we do our exams, we don't have to manually calculate it. Okay. Because it's really time consuming. Now we can use a computer, we can do everything. So I will show you how to do this calculation in the stack branch. Okay. But here, that's the underlying probability mass function model. That's the model we use. Okay. So that's for the binomial distribution. So let's see one example. Okay. Let's see one example. So 2 successes in 5 trials. Okay. We have 5 trials, and we are interested in 2 successes. Okay. So for each trial, the probability of success is 0.1, 10%. Okay. Each trial has the probability of success 10%. Okay. We want to know the probability that we have 2 successes out of the. Okay. So let's define the parameters. Okay, we have the P 10%, 0.1, right? And Q 1 minus P, so that's the probability of failure, right? 1 minus P. 0.9, and N is our total number of trials. In this case, we have 5 trials. K, number of successes. Okay. Then if we plot the numbers in this model, okay, so we can do some calculation by hand or calculator and so on and so forth. We can have this probability. The probability of having 2 successes out of 5 Bernoulli trials. So the probability. This is the probability. So any questions on this model? two important information. The N, what is N, what is P? The P is the probability of success, right? So that's, we already defined that when we talk about the probability trial. And the other parameter, important parameter is the N. N is the number of total number of trials, okay? So let's do not confuse with the number of trials and number of successes, okay? So the parameter we need to use here, N is the total number of trials. And the K here is the number of successes. So this is very important. When you use the stack crunch, let's use the correct number. So you need to put this total number of trials and into the stack crunch, not this one. Okay? We'll show you that later. Any other questions before we go to the stack crunch? Still, if we want to calculate some probability, let's go with this step, and also under this calculator. Throughout this chapter and the next chapter, we will deal with a lot of distribution calculators. So you can find all those calculators under this category. That's calculator. And now we are working on the binomial model, right? So let's click this binomial. Okay. Stat calculator binomial. So similar to the geometric model calculator, we have a similar interface. Okay? Then let's focus on the standard one. Okay? So as you can see, we have two parameters, N and P. Okay? Again, N is the total number of trials, and P is the probability of success. So if we go back here, so N is equal to 5, right? We have total number of trials, 5. And the probability of success is 0.1. And we are interested in the probability of having exactly 2 successes. Okay? So you have to change it to equal. Okay? And if I put the 2 here, okay? So that's where you put the K, the number of successes. Okay? So that's much easier, right? Than doing the calculation by hand. So that's how we use this binomial calculator to find the probability of the number of successes is equal to a certain number. Or you can change this to less than or equal to. So that gives us the probability of seeing the number of successes of 2 or 1 or 0. Yes?
How do we know whether to put equal to or less than or greater than?
Okay. So how do we know if we need to have the equal to or less than or greater than? Okay. So that depends on the question. So if you are interested in, okay, I just want to know what's the probability of seeing 2 successes, exactly 2 successes, you just use the equal. But if you are interested in what's the probability that I can see at least 2 successes? So if that's the case, which one should we use?
Less than.
Less than or greater than or equal to, right? So that really depends on the question or what's that?
How the question is worded.
Yes. Yeah, so that you may have some questions asking exactly 2 successes or 3 successes, or at least 2 successes, or no more than 3 successes. Okay? So that's when you have to change this from equal to greater than or to less than or so on and so forth. Okay? Any other question? and that's between. So what if I'm interested in the probability that the number of successes is between 2 and 4? Okay? So that's when we use this between. Okay? Still, we don't change those two parameters. Okay, we don't change that, but we change this one 2 and 4. Okay? We are interested in 2 successes, 3 successes, and 4 successes. Okay? So that's when we use the between. Okay? Yes.
So on a home, what would it actually, what is they cancel if they want to, you know, put, what kind of question are you asking?
So what kind of question? So most of the question will tell you, okay, you need to use a binomial model. And you need to calculate the probability of x is less than, say, 2. Okay, that's the question you may have. Most of the question will be like that. But in some cases, you may have the question like, you are given a description like the one we discussed last week. So you may have a question like this, but this one is about geometric model. But you may have a similar question that where you need to use the binomial model. So what if I change this question? I change the question to that. So what is the probability that he closed 4 deals out of 9 trials? So in this case, we are talking about binomial model, right? So you need to be careful when we have a problem description, and the question didn't tell you you need to use the geometric model or binomial model. Then you have to identify, do I need to use the binomial model or geometric model? So how to identify which model to use. So last week we said, when we talk about geometric model, so the keyword, what is the keyword we need to catch in order to use the geometric model?
The first time?
First time, first success, okay? Or something like this. He fails to close for the first time, okay? Some similar keyword like that. Then you know it's talking about geometric model. Okay. But if the question is like, okay, what's the probability that he or she has 3 successes? In that case, we are interested in the number of successes, right? So in that case, we know whether we need to use the binomial model, because binomial model is dealing with the number of successes out of the total number of trials. Okay. So if I change this to what's the probability that he closed 4 deals out of 9 trials? So if I need to work on that. Where's my step? Okay, here's my step. So still, I need to change the parameters, right? I said I have 9 trials, right? I tried 9 times. Let me put 9 there. And the probability of success, let's use a number here. So that's 75%. And I said I'm interested in exactly 4 successes. 4 successes. Then that's the probability. So the same question, based on the same description, based on the question I asked, you can use geometric model or binomial. So are we clear about how to identify which model we need to use? Any questions? So that's the binomial model. let me ask you one math question. So we have this factorial, right? So what is value for this? 0 factorial. Okay, remember this is equal to 1. So in your homework, you don't need to do this calculation. But in case you need to use this calculation in other classes, the 0 factorial is equal to 1. Okay. That is one additional information. And some properties for binomial. Okay. The mean and also the standard deviation. So as you can see, those two properties are based on the two parameters, n, which is the number of trials, okay? And p is the probability of success. Those are the two properties we need to remember for the binomial model. We have one more model to discuss for this chapter. Okay. So this binomial model and geometric model, both of them are based on Bernoulli trial. But the next one, the Poisson model, is not based on the Bernoulli trial. Okay. So what is Poisson model talking about? Okay. So that's a discrete model often used to model the number of arrivals. Okay. So for example, customers arrival. So if you are running a restaurant or some like a McDonald's, Burger King, or Pizza Hut, so you want to know how many people you need to put there. So in order to determine how many people you need to hire, you have to know the behavior of the customer arrival, right? But if you, every 1 hour there's only one customer comes, you don't have to put 3 or 4 people there. Okay? So that's why we have to model the customer arrival. And to model that, let's use the Poisson model, Poisson distribution. So this is, let me ask you again, what is this? This is the probability what function? This is a probability math function, right? So in the next chapter, we will have discuss another probability function. So we need to know the difference. So this is the PMF for the Poisson model. And for this model, we have one parameter, which is lambda, the Greek letter lambda. So lambda is the arrival rate. This is the arrival rate. And in this model, the E is a constant. Okay? The E is a constant. It's not a random variable. It's a constant. So we use this model to describe the customer arrival. For example, the call center. You want to know what's the probability that within 1 hour you will have 3 phone calls or 4 phone calls. So that's the model we need to use. Okay? The Poisson model. So let's see one example. Suppose we want to know the probability of no hits for a website. Okay? We want to collect some data on customers clicking on our website. Okay, so that's the scenario. And the mean rate, we know the rate. The mean rate is 4 hits per minute, which is 2 hits per 30 seconds. thing we need to do is to define our parameter. In order to use the Poisson model, we only have one parameter to define, right? The lambda. And based on the description, we have 4 hits per minute, but the duration we are interested in is 30 seconds, right? That's the parameter. That's the duration we are interested in. Okay. Then the lambda is equal to 2 hits per 30 seconds. So lambda is equal to 2. And if we put the model in there, so we are interested in what's the probability that there's no hit in the next half minute. Okay. So that means x is equal to 0, right? So when we plug the numbers in there, we can do the calculation by hand, or later on I will show you how to do this next time. Okay. So that's a probability. But here, what we need to do is that based on this description, we want to know 2 things. First one is the parameter, the lambda. What's the lambda? The lambda is 2 hits per second, per 30 seconds. So lambda is equal to 2. And how many arrivals are you interested in? In this case, we are interested in 0 arrivals. But you may be interested in 1 arrival or 2 arrivals. Okay, so that's based on the question. So that's how we plug numbers in this model. Okay? So from this model and we plug numbers in. So any questions before? Yes.
So E is always going to be 2.71828.
Well, can you say that again?
So E is always what it is.
Yeah, it's always E is always that number. That's the constant. Any other question? So let's find the E limit. So let's close this binomial calculator. And still under the stat calculator, we have this total calculator. Again, all the calculators are under this stat calculator. And Poisson. So this is the question we are interested in. The mean, okay? The parameter is the mean, lambda. And in this question, the mean is 2. And we are interested in there's no hit. So that's why we have to change it to the equal to 0. Okay? We are interested in 0 arrivals. Okay? In the next half minute. Okay? Yes.
So the mean will always be given text?
The mean is always given to you. Okay?
Okay.
If you do not know the mean, there's nothing we can do.
Okay.
Right? Any other questions? Yes. So if that's the mean is we have a few numbers here, right? So that's a very good question. So it says 4 hits per minute, right? And what is the duration we are interested in? We are interested in the probability of no hits to the website in the next 30 seconds. Although the given information is about 1 minute, but we are interested in half minute, right? 30 seconds. So that's why we have to manipulate the information a little bit. So if we have 4 hits, on average, we have 4 hits in 1 minute. So how many hits do we have in half minute? 2, right? Half of the 4, right? So that's why we have to be careful about what is the duration, what is the horizon we are interested in. Okay? So that's why maybe this number doesn't match with the horizon. So that's why we have to manipulate the numbers a little bit. Does that answer your question? So that's why we, in the stack count, we said, and here, also here, we have the lambda is equal to 2, and in the stack count, we use the mean is equal to 2. Okay. Any other questions? So given this description, so how do we know it's about Poisson model? Okay. So we already learned all the models. We need uniform, okay, geometric, binomial, Poisson. How do we know it's talking about Poisson model? So that goes back to the definition of Poisson model. Okay. Poisson model deal with arrivals. So arrivals may mean different applications. Phone calls coming, customers coming. Okay. So those type of applications. And again, this Poisson model is not about Bernoulli trial. Okay. So if you see this description, so there's no probability of success or failure, right? So that, and it's talking about arrival. What things are arriving? Hits. Okay. Hits on the website. So that's about arrival. So after reading this description, if you realize, okay, this is about something arrival. Okay? So then you need to know if this is to use the Poisson model, and also you need to have a mean rate, arrival rate. Okay? So combining those two things, you will know, okay, this is about Poisson model. Okay? So this question. Website manager has noticed that during the evening hours, about 3.4 people per minute check out from their shopping cart and make an online purchase. So she believes that each purchase is independent of others and wants to model the number of purchases per minute. So which model are we talking about here?
Poisson.
Poisson. Okay. So how to pronounce that? Poisson or Poisson?
We just call it poison?
Based on what I learned, it's called Poisson. Yeah.
I'll get it.
It's not poison. But if that helps you to remember that, you can use the poison. Okay. Here we are talking about Poisson model, right? Why is that? We are talking about arrivals, right? What are the things arriving here? Checking out, right? Customers checking out. So that, although it's not there's no we have word like arrival, but we don't have any keyword like arrival, right? But we know it's talking about something arrival, right? So that's how we know it's talking about Poisson. So what's the probability that in any 1 minute at least one purchase is made? So let me invite someone to here to do this calculation. Okay? So any volunteer? Any volunteers?
We can do it, but I don't know if we're doing that.
Can you
Sure.
You wanna come?
Alright. So head over to the little stat right there.
Okay.
Calculator. Poisson.
Okay.
is where I get a little confused. So like you have, cause like you can't, nothing of that transferred over here, did it? Or did it?
So all the numbers you need are directly from the
Right.
equation.
3.4 per minute, so it'd be. I know what your mean would be.
So
I mean, 0.4.
what is the mean?
3.4.
It's 3.4, right?
So the mean's 3.4.
Yeah, 3.4.
And then P would be, that number right there would be, 1.
So what is the question?
What is the probability that in any 1 minute, at least one purchase is made?
Okay, at least one purchase. So should we use the equal or less than or greater than or less? What was that?
I believe it should be greater than or equal to.
And how many purchases?
Just 1.
How about let's put the number in the set function.
In the thing, or?
Yeah.
Okay, yeah, all right.
Excellent. Thank you. Okay, we have one more example. Okay. Thank you very much. So we have,
I have a question.
yes.
So with each different model, is that like how you know which how to do it in the step one? Like,
So
which one you use?
so that so how do we know which model we need to use, right?
Yeah, and I'm saying once you know which model you need to use, cause I seen how he went in stack crunch and he like chose that specific one, so is that like what we do for each model? Like if it was a geometric one, you would choose geometric in stack crunch?
Okay. Let's finish that question, then we will show how to do it by using other model. Okay. So next question. What's the probability that no one makes a purchase in the next 2 minutes? So this question is a little bit tricky. How about you guys tell me how do I do the calculation? First of all, what does it mean?
3.4.
For 4.4? Oh, so 3.4? 3.4? No. So everyone agrees 3.4, right?
Yes.
And here, so we will see if there's any difference between the equal or less than or equal to. Yeah. And there's 0. No one makes purchase, right? So we have this one, and if we choose this less than or equal to, it's the same. So let me put this 0.33. So let's read this. Let's read this question again with the information we have. I said this question is a little bit tricky. So what is the information we have from the description?
3.4 people per minute.
So that's 3.4 people per minute, right? And what is the question asking?
2 minutes.
2 minutes. So what would be the mean?
6.8.
double that, right? Point 0.0011. So it's not that difficult, but you have to be careful for this kind of question in your homework or in the exam. Okay? So any questions on this one? So this is about Poisson model. We know based on the description, we know, okay, we are talking about Poisson model. Then we can go to the stat function, stat calculator, and we select the Poisson calculator to our calculation. And if we go back here, so the example we did last time. So based on this description, we already know that there's a keyword first time. Okay? We know we need to use the geometric model. Okay? So then we have to go back here to use the geometric model. So this is a geometric calculator. Then based on the description, let's figure out what is the parameter, what's the probability of success. Okay? Then we put the numbers in there, okay? Then we can do the calculation. So that's for the geometric model. And if we know, if the question is, so we already discussed that. So what if the question is, what's the probability that he closed 4 deals out of 9 trials? Then we know we are talking about binomial model, right? Then if we know, okay, we need to deal with the binomial model. Then let's go to the stat calculator. Let's choose the binomial calculator. How many number of trials? 9 trials, okay? And what is the probability of success? 0.75. And we are interested in exactly 4 successes. Then we will have the number. Okay? So that's for most of the questions. So if you know we are talking about some of the models, we can use the calculator in the stat function. And another one we didn't talk about is the uniform. Let me see this. So you see there's a uniform, right? However, this is for the continuous uniform distribution. So this is not for the discrete uniform distribution. Okay? So that's why we didn't discuss it. So here in this chapter, for the in this chapter, we are talking about discrete probability models. Okay? So we have the calculators of binomial, geometric, and Poisson. So we have questions in the homework and exam. You can always use the calculators in the stat function. Any questions before we go to the next chapter? Okay. So that is all about chapter 6. So in chapter 6, we are talking about expectations, variance, and the properties of expectations and variance, and also we talk about 4 discrete probability models. Okay? And the next chapter, we need to talk about continuous distribution. Okay? So by the way, the next exam will cover chapter 6, 7, and 8. Okay? So we will starting chapter 7 this week. Hopefully we will finish chapter 7 by next Tuesday, and we will have one more chapter, and then we will have the second exam. So you guys still remember the Z-score, right? No? Well, I highly doubt how you did the questions in the first exam. So this score, so this is the formulation we use to calculate the Z-score, right? We have the mean, we have the sample standard deviation, and this X is the specific value we are interested in. Okay? We want to find the Z-score for this value. Okay? So that's the model we learned in the previous chapter. So we need to, in this chapter, we will most of the time we will deal with this kind of distribution. So this is a unimodel, okay? And you have one bit, so it's unimodel. And symmetric, if you fold this picture here, so you will have the mirror image. So this, we are, most of the time we are dealing with this kind of distribution in this chapter. Okay. So that's where we start to talk about the 68, 95, and 99.7. Okay. So what is this rule about? So for this kind of distribution, we have two parameters: the mean and standard deviation. Okay? The mean and standard deviation. So in this figure, the mean we have that as 0. It doesn't have to be 0, but it could be 1 or 2, any number. But we need to have a mean. Okay? That's one parameter. The second parameter, standard deviations. So in this figure, we have from here to here, that is a 1 standard deviation away from the mean. And from here, this is a 2 standard deviations away from the mean. And here is also the same. And 3 standard deviations away from the mean. So this rule is talking about 68% of the area under this curve is within the 1 standard deviation away from the mean. Okay? So that means this area accounts for 68% of the whole area. Okay? And if we are talking about the area within 2 standard deviations away from the mean, it covers 95%. And if we are talking about 3 standard deviations away from the mean, that will cover 99.7% of the whole area. So this is a distribution. We know that the whole area must be equal to 1. So that's a probability, right? That's a probability. So that's this rule talking about. Okay? So we have some real applications of this rule. Okay? So we will talk about one of our applications in the later slide. Again, this rule only applies to unimodel symmetric distribution like this. Okay? So if you have other distributions which is not in this type of shape, this rule doesn't apply. Okay? Any questions? Next, we will talk about a very, 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 very important distribution, normal distribution. First of all, this is a continuous distribution. Continuous distribution means that we can pick any value. Okay. But in the discrete distribution, we can only select a certain number of values. So this is a normal distribution. We have two parameters. We talk about. We have the mu, which is the mean, and we have the standard deviation sigma. So sigma is our standard deviation. So for this slide, we need to know what does a normal distribution look like? It's a unimodal symmetric bell-shaped distribution. But it doesn't mean all this type of distributions are normal distributions. So in the later chapters, we will learn another T distribution, which is also like this shape, but it's different. So this normal distribution, we have two parameters. If you identify the distribution is normal distribution, you have to have, they need to tell you, okay, this is a normal distribution. Okay, they need to tell you. So based on the figure or the chart we just saw in the previous slide, we cannot say this is a normal distribution. Okay? They have to tell you. So this we have two parameters, mu and sigma. Okay? So this is one piece of information about normal distribution. So let's put the standard deviations. So this is a normal distribution, and if we apply this 68, 95, and 99.0, we will have this kind of thing. And what is the real application? So one application is the concept of Six Sigma. So any of you heard of this concept, Six Sigma? So when you take so if you are a management major, if you take the production and operations management or other like the supply chain management, logistics, you will learn this concept. Okay? So this Six Sigma concept is from what we just discussed. Okay? So that's a quality focused methodology. So when we do our manufacturing or we provide our service to our customers. For example, we manufacture this clicker. The length of the clicker, let's say 3 inches. Let's say 3 inches. So when we manufacture this one, we make hundreds, thousands of this product. Okay. So we want to. Our target, our hope is to have the length to be exactly 3 inches. But in reality, that's really hard. But we want to control our quality. So that's why we have some variation about the length, but it cannot be too far away from 3 inches. Okay? So that's why Six Sigma means that the dimension or the measure of your service or your product have to be aligned with this Six Sigma. That means you have to make sure that the length or the quality of your product is within Six Sigma area of the mean of your target. Because for example here, for this clicker, my target is 3 inches and I have some standard deviation, but I need to make sure that 99.999% of my products, their length have to be within Six Sigma in that area. Okay? That means this is where Six Sigma is. So for example, the mean is 3 inches. If I produce a clicker, the length is here. That means it's defect. So that's why I have to make sure 99.99999% of all my products should be in this area. Okay? So that is one application. So if you are interested in when you take the course, you can have more details about that. Okay? So the normal distribution. Okay? So that's in the normal distribution, the mu can be any value. Okay? Could be 1 to 100, 300, and so on and so forth. Okay? Standard deviation also we can have different numbers, but we need to know some properties about this kind of distribution. But if we do not control the mu and sigma, we don't have a standard property. So that's why we have a standard normal distribution. So for this standard normal distribution, the mu is 0, the standard deviation is 1. Okay? So that's standard normal distribution. Okay? In the regular normal distribution, the mu can be anything. The standard deviation can be any value. But for the standard normal distribution, the mu has to be 0 and the standard deviation has to be 1. And for this model, we have a lot of information. We know basically everything about this model. Okay? So if someone gives you a number 2, okay, and they ask you to calculate what's the probability that the random variable is less than or equal to 2. So you can directly find the probability. Okay? So that's why we have the standard normal distribution. So one thing you need to remember is that for the standard normal distribution, the mu is equal to the mean, the mu is equal to 0, and standard deviation sigma is equal to 1. So that's what you need to know from this line. Okay? So how do we convert or transform a regular normal distribution to a standard normal distribution? That's where we use this formula. So the very first line, okay, we review this formula. So this is a regular normal distribution with the mean of mu and standard deviation of sigma. Okay? And you can transform or convert this regular normal distribution into a standard normal distribution. Because when we talked about the this work, we said when we do this standardization, when we calculate this work, it doesn't change the shape of the distribution. Okay? So any properties in the original distribution, we will still have it after this transformation. So that's why sometimes here for the regular normal distributions, we use the random variable x, right? Because we use this formula. So that's why for the standard normal distribution, we use the letter V to denote a random, standard normal random variable. Okay. So this is the formula we use to transform a regular normal distribution to a standard normal distribution. Any questions? So this is a new concept. Okay. Probability density function. So when we talk about the discrete probability model, we said, okay, the distribution have the PMF, probability mass function. But for the continuous random variables, we do not call it PMF, we call it PDF, probability density function. So that's the function of any continuous model, probability model that gives the probability of a random value falling between any two values. So it's a small f of x. One important thing need you to remember is that this PDF, this probability density function, does not give the probability for a specific value. So when we discuss the discrete random variables, the probability models, we said the PMF, the probability mass function, gives the probability of the random variable equal to a specific value. Okay? So PMF, that gives us the probability of a specific value. But this PDF does not give the probability for a specific value. So that's one thing I need you to remember. If someone asks you, what's the probability that a normal random variable is equal to 1? It's always 0. If I give you a random variable, the random variable follows a continuous normal distribution. What's the probability that the random variable is equal to 2? The probability is 0. What's the probability the random variable is equal to 100? It's also 0. Okay. So for that gives us the last thing. For continuous random variable x, the probability of the random variable equal to a specific value is equal to 0. Right? So those two statements we have to remember. So those are different from the discrete random models. So why this is true? So for example, we have a random variable, normal distribution. Okay? Mu is equal to 1, and standard deviation is equal to 0.5. Why is this? Why this is true? So let's look at this curve. So this is a regular normal distribution. We know that the whole area under the curve, that's equal to 1, right? That's equal to 1. And what is the probability that the random variable is equal to a value between the mean and one sigma?
The 19.1.
So is this area, the value of this area, right? Is this area, okay? So that's a range between the mean and one sigma. So if we cut it half, let's say this range is half of is this area, right? Then if we are talking about a specific value, so we have to further shrink. Then if we are talking about a specific value, the area for that value is 0. So that's why we have this statement. The probability of the random variable is equal to a specific value is equal to 0. So that's why we have this statement. Let me see. So we will continue this discussion on Thursday. So if you haven't signed the row sheet is here.